Hello everyone. Welcome back to the microwave lecture series. In last lecture series we discussed about the types of transmission lines. In this lecture series we'll discuss about the equivalent circuit of transmission lines. Before going to this equivalent circuit model, so let us look a close look of the types of transmission line model. Here it is a two-way transmission line model. In two-way transmission line model also we have the two conductors and there is a dielectric material, there is an air gap between these two conductors. So I have already discussed about this. In next we'll see of the coaxial cable. In coaxial cable is also we have this two conductor model. So again we have this dielectric. There is an air gap between this thing. Next we'll see about the microstrip transmission line model. In microstrip transmission line model, we have this two dielectric two conductor, that is of top conductor material, and this bottom is also copper conductor material, which is separated with the dielectric material. So in all this three transmissions whatever we discussed earlier, we have this two conductor wire material. So based on this we'll derive the equivalent circuit model. So in last we have seen this all the types of transmission line is a two wire conductor. There is two conductor model. So based on this we have drawn this equivalent circuit model. So this equivalent circuit model, let us see this. We have placed this R resistance components. For this resistance is we have used because we have if any signal when it is transferred, there will be this signal loss due to this heat. That's why we have mentioned this R here, and this inductance L is due to this magnetic effect, that is we are using the microwave frequencies. So we have this large amount of magnetic field, magnetic conductance effects. That's why we have mentioned this inductor of L. And here is because of this two wire, that's why we have mentioned this R and L, and here is also an RLL component. And this two wire conductor is separated with a dielectric material. And this separation between these two copper plates, so that's why we have mentioned this C. And here G is a conductance components. We have used G because we may occur the loss in the transconductance component. So based on here we have, this is of the infinite transmission line model. So here instead of taking this infinite transmission line model, we have taken this equivalent circuit of transmission line model in this del L. Del L is with separate part of this transmission line model. Here we are passing the signal. So this, when the signal is transmitting to this load, and here for calculating this characteristics of transmission line model, here you can see this. I have used only this top line because when we go for finding the characteristic impedance of this particular wire, that is of particular distance, then we have to measure the signal with respect to the ground plane analysis. So with if we go for the ground plane analysis, so it is not required to mention this R and L component. So that's why we have mentioned this is a plain line component. And here we are using del L of separately of particular transmission line, particular distance thing. So that's why we have mentioned with all the components of R and del L, and inductance of L and del L, and this conductance is of C and del L, G is also del L. So here we assume that for any we assume this for lossy transmission line of component, this R and G will be very small. So that's why this R and G will become a lossy component thing. So this is the characteristic impedance of transmission line model. This characteristic impedance here will measure of this approximately of infinite transmission line. For any infinite transmission line, the characteristic impedance will be of Z0 is equal to root of R plus J omega L divided by G plus J omega C. For any lossless transmission lines, because R component, G component is very lowly, we can make a zero, negligibly conductance power. So that's why we make R and G as in 0. So when we make RG as 0, we get will be of Z0 is equal to root of L by C. So here you can see this when the power will go inside. So that's when we are giving the supply. So here in this Zin, that is the input impedance of characteristic input impedance. So this Zin should be equal to the Z0 of the transmission line impedance. When this two transmission impedance will get matched, then only we can able to transmit the current to this entire transmission. Otherwise, if there is a mismatch condition now is occurred, we cannot able to transmit the power thing. So based on this, we'll see the will derive the standing wave ratio, voltage, reflection coefficient ratio. Everything will derive based on this Zin and Z0. Similar to this in the output thing. So this Z0 will should be equal to the ZL. So when this impedance of Z0 and ZL output to this load is matched, then only we can able to receive the power at the other end. Otherwise, now as an output. So otherwise, again it will, if the mismatching is occurred, we cannot able to transmit the entire power effectively to the entire transmission line. So this Zin and Z0 impedance like mismatching thing and matched impedance and unmatched impedance will discuss in the next lecture series.